Good afternoon, everyone. My name is Christo Merriweather Keller, and today I'm going to be talking about enumerating k-Naples parking functions. This is joint work from a paper that I wrote with Laura Colmenarejo, Pamela E. Harris, Zakaya Jones, Andres R. Vindas Melendez, Andres Ramos Rodriguez, and Eunice Sucarto for the 2020 AIM-UP program and the UMass Math REU. So before we can talk about enumerating k-Naples parking functions, I'd like to spend a moment talking about just what parking functions are. So k-Naples parking functions were defined in Christensen et al. 2020 as a generalization of the Naples parking functions from Baumgartner 2019, which in turn generalized the classical parking functions in Konheim and Weiss 1966. So nowadays we call the classical parking functions 0 Naples, and the Baumgartner parking functions the 1 Naples. And Christensen extended this to all positive integers k. So what is a k-Naples parking function in general? It's a way for n cars to park in a street with n parking spots, subject to the following parking rule. So there are n cars traveling down a street with n parking spots. Each car wants to park in a particular spot. The car likes a spot. As it comes in, it tries to park in that spot, and if it's empty, it parks there. Otherwise, it tries to parallel park up to k times behind it. And then it continues forward and sees if there's any spots in front of it that are open. If all the cars park successfully, the vector of parking preferences for each car is called a k-Naples parking function of length n. So what are some examples of these things? A permutation, member of the symmetric group, is k-Naples for all k. So if all the cars want different parking spots, then they'll all come in and all their spots will be open because each spot only shows up once in the permutation, and all the cars will park. For a better example, a more interesting one, 3133, which is not a permutation, is 1 Naples. It's a 1 Naples parking function of length 4. So the first car comes in, and it wants the third parking spot. But none of the spots are taken, so it just parks. Then the second car comes in, and it wants the first parking spot. That's also not taken, so it just parks. Then the third car comes in, and it wants the third spot. But the first car has already parked there. This is 1 Naples, so it can parallel park up to 1 times. So it tries to parallel park, and it succeeds parking in the second spot. And then the fourth car comes in. It also wants to park in the third spot. That's taken. It tries to parallel park once because this is 1 Naples, and it fails because that spot is also taken, and so it continues forward and parks in the fourth and final spot. You can see this would not be a 0 Naples parking function, because when the third car came in the 0 Naples case, it wouldn't be able to park in the third spot, which was already taken by the first car. And so it wouldn't be able to parallel park because it's 0 Naples, and it would continue and it would park in the fourth spot. And then when the fourth car came in and sees the third spot is taken, it can't parallel park, it'll continue, try to park in the last spot, that's not taken, and then it'll drive off the road not having parked. In fact, every parking preference is k-Naples for a sufficiently large k. If you take k equals n-1, then every car checks every spot, because it checks at least its own spot and all the spots behind it, which there's up to n-1 of, and all the spots after, because they always check all the spots after, if they don't park immediately or parallel. Now, how many k-Naples parking functions of length n are there? So we can start with the easiest case, the classical case where k equals 0. It's a well-known result that this number of 0 Naples parking functions of length n is n plus 1 to the n-1, which looks like Cayley's formula with n plus 1 plugged in. So in fact, this gives a bijection between 0 Naples parking functions of length n and labeled rooted trees of length n plus 1. Now, labeled rooted trees of length n plus 1 are in bijection with labeled rooted forests of length n. And so we get some bijections like that, which were explicitly given by someone named Schutzenberger. However, the best we have for k-Naples in general is this rather unwieldy recursion, that the number pfnk of k-Naples parking functions satisfies this relation, which isn't very nice. So what can we do to try to count them a different way than Christensen did? We filter the count by the outcome. So for each way the cars finally park, how many ways could they have parked that way? This will let us use the parking rule and proceed by cases. So let's try an example. Suppose we want to know how many k-Naples parking functions park the cars in spots 2, then 4, then 5, then 3, then 1. So that the parking spot at the end has the 5th car in the first spot, the 1st car in the 2nd spot, the 4th car in the 3rd spot, the 2nd car in the 4th spot, and the 3rd car in the final spot. Well, the 1st car is the first to come in, and it ends up in the 2nd spot. So it couldn't have backed up, it couldn't have moved forward, it just had to park there. There's only one option. Car 2 has the same deal. It parks in the 4th spot, but the 5th and the 3rd aren't taken, so the only way it could have parked there is by driving in immediately. Now car 3 has to choose the 5th spot, but now it has two choices. It can either have wanted to park there, or have wanted to park in spot 2 and moved forward. But in that case, it would have backed up into spot 3. So again, there's only one option. Car 4 has some choices. It can choose 3, 4, or 5. Because if it chooses 3, it just parks. If it chooses 4, well, 2 is already there, so it backs up once. If it chooses 5, well, 3 is already there, so it backs up once, but 2 is already there, so it backs up twice. It can back up to twice because it's k-Naples. So there's 3 options. And similarly, car 5 has 3 options, which are about the same idea. So the total number is 9 functions by multiplying these choices together. And so that's the idea. We're going to count the number of choices, multiply them together, and sum them over all the number of parking lots. This is an example of the choices a car could have to make. This car wants to park in this spot, and so it can try either the 4th spot or any of the first 3. That'll work for k equals 1. But in case 2, it has to be careful. It can't choose that 2nd spot, even though it's already taken, because then it'll back up into the wrong spot. And so we have to worry about these cases. And so we define this L to be the number of choices using that logic. And we get the theorem that the number is the product of these L's summed over the symmetric group, which is the number of parking lots. So a parking lot ends up being a permutation because no 2 cars park in the same spot, all the cars park in some spot, so it's a bijection on the set of the first n numbers. In fact, we go further, and we show that the Q analog, which is the number turned into a polynomial in this way, such that the limit of the polynomial is the number itself, with some extra information thrown in, is, in fact, the distribution of the area statistic over the parking functions. And this generalizes to the k-Naples parking functions by generalizing the area statistic to the k-Naples parking functions in some way that preserves this property. And we define that in our paper, which is the 3rd paper here in my references, counting k-Naples parking functions through permutations in the k-Naples area statistic in enumerative combinatorics and applications, Volume 1, Issue 2, Article S2R11. So I hope you check that out. Otherwise, I hope you at least learn something, see that the generalizations of the parking functions are interesting in their own right, and thank you for listening to my talk.